To truly understand the mechanical reality of the T-34, we must look closer. Not at the sweeping armor, but at the absolute micro level. It begins with a single M24 steel bolt. 6 of these precisely machined bolts are required to secure a single central hubcap, torqued down against immense vibrational stress. This hub holds the core of the Christie road wheel. Rather than a solid casing, the 830mm diameter wheel was formed by stamping 2 convex, 15mm thick steel discs, which were then permanently fused together at the circumference by a continuous 10mm wide submerged arc weld bead, creating a lightweight but incredibly rigid hollow structure. Over this welded rim, a 50mm thick solid ring of vulcanized rubber was hydraulically pressed into place to dampen high-frequency track vibrations. Inside the hub, the entire 830mm wheel spins on 2 massive tapered roller bearings, heavily packed with thick industrial grease to survive the abrasive dirt of the battlefield. This entire wheel assembly mounts directly onto a solid forged steel trailing arm. There are no delicate hydraulics here, just raw, unbreakable mechanical leverage. That leverage transfers directly upward into a coil spring wound from high carbon steel wire measuring an astonishing 40mm in diameter. To put this power to the ground, the tank utilized a 72-link track belt. Each individual link was a single 13.5-kilogram piece of solid cast steel, complete with a 100mm tall guide horn. But the true genius lay in the connection. The links were joined by a perfectly smooth 22mm steel pin. There were no bolts, no nuts, and no securing heads. It floated completely freely. Because it was unsecured, intense battlefield vibration naturally caused the steel pin to slowly back its way out of the hinge, threatening to snap the entire track belt. The solution was delightfully brutal. A sloped steel cam plate was welded directly to the rear hull. As the track rotated past, the plate simply smashed the protruding pin violently back into place. This eliminated the need for complex locking nuts or cotter pins. It was a self-correcting, fully mechanical loop that relied entirely on raw physical impact. When you pull back from the microanatomy, you see the true genius of the system. From the 24mm bolts to the 40mm springs and the self-hammering track pins, every single component was engineered with brutal, unapologetic simplicity. A foundation built not for comfort, but for absolute mechanical survival. Moving from the suspension tracks, we deconstruct the armor itself. The T-34 survival relied on how its plates were cut and fused. It begins with the raw, flame-cut edge of a 45mm plate. At a microscopic scale, this plate is a dense iron matrix. Soviet metallurgists formulated the MZ2 steel with 0.3% carbon and 1.5% manganese to optimize surface hardness. To maximize structural strength, the edges were not left flat. A machining tool cut a precise 45-degree bevel along the plate's perimeter. These beveled edges allow the front glacis and side plates to physically interlock using interlocking dovetail joints, mechanically binding them before any welding began. When interlocked, a precise 5mm gap remained at the root of the joint. This gap was engineered to receive a massive torrent of molten steel. To fill this gap at industrial speed, manual welding was replaced by the patent automatic welding head, feeding a continuous 5mm thick steel wire electrode. Before ignition, a copper funnel deposited granular flux powder over the joint, completely burying the 5mm gap under a layer of protective silicate mineral stones. Submerged beneath the powder, a 1,000-ampere electric arc ignited. Without blinding glare or open flame, it generated a localized zone of 1,500-degree heat. The intense heat liquefied the wire electrode and the beveled plate edges simultaneously, blending them under a boiling shield of molten protective slag glass. As the welding head moved forward, the molten slag cooled into a brittle, glass-like brown crust. A mechanical chisel tapped the crust, causing it to shatter and flake off cleanly. What emerged was the finished weld bead, a continuous row of thick, overlapping metallic ripples, fused 30mm deep into the root of the joint. Internal stress vectors prove that this automatic fusion altered the crystalline structure, making the welded joint mechanically stronger than the parent steel plates themselves. By repeating this automated cycle across every seam, the individual plates merged into a monolithic, watertight armored tub, an indestructible steel vault. Inside this vault, heavy 20mm thick steel mounting lugs were welded directly to the interior walls, providing the exact alignment holes for the upcoming suspension hardware. This rigid sealed hull was now ready. The logic chain demands a foundation capable of isolating this immense mass from the violent impacts of the terrain. It was time to install the Christie springs. With the monolithic hull welded shut, the suspension had to be integrated into the remaining double-walled side cavities. This required 5 vertical steel sleeves per side. To protect the 40mm thick high-carbon springs from dirt and internal damage, each coil was sealed inside its own cylindrical steel housing. These encased assemblies were then dropped directly into the vertical shafts of the hull, anchoring firmly to the upper armored deck. But here lies the genius of the Christie system. The spring compresses vertically inside the hull, but the wheel must mount horizontally on the outside. The solution was the bell crank. A heavy splined pivot shaft was driven horizontally through the thick outer armor, entering internally to an upward-pointing steel cam. This cam rested squarely against the bottom plate of the vertical spring. On the exterior, the massive forged trailing arm was bolted to the same splined shaft, pointing backwards to receive the wheel axle. Through this simple bell crank linkage, violent horizontal shocks from the terrain are mechanically translated into vertical compression inside the protected hull. With the shock-absorbing core mapped out, All 5 of the massive 830mm road wheels were secured to the trailing arm axles. Secured by the M24 steel bolts on the central hubcap, the wheel assembly was completely frictionless, yet mathematically indestructible. Around these wheels wrapped the massive track belt. Notice the deliberate absence of return rollers. A catenary curve dictates how the heavy track simply sags and rides directly atop the road wheels. At the extreme rear, kinematic diagrams show the drive sprocket's teeth perfectly intersecting the tall steel guide horns of the track links, ready to transfer engine torque. At the front, adjusting the internal tensioning screw pushes the idler wheel forward, instantly pulling the entire track schematic perfectly taut. Under extreme dynamic load, maximum suspension travel is halted by a physical bump stop on the hull, mathematically preventing the trailing arm from shattering the chassis. The lower foundation was now complete, a geometrically perfect, shock-absorbing platform. All it lacked was a power plant, capable of generating the required torque. To drag 26 tons of steel through freezing mud, the chassis required a monstrous power plant. This is the legendary V2 engine. Originating from aviation designs, the massive block was cast entirely from aluminum alloy. This incredibly expensive material saved hundreds of kilograms, weight that was reinvested directly into the thick steel armor. Here, the mechanical logic chain is absolute. The 2 cylinder banks are angled at exactly 60 degrees, perfectly mirroring the 60-degree inward slope of the outer hull armor. Inside the cylinder heads, its aviation heritage is undeniable. It utilized dual overhead camshafts, driving 4 large valves per cylinder to maximize volumetric airflow. Nestled perfectly between the cylinder banks was a high-pressure mechanical injection pump, forcing raw diesel fuel directly into the combustion chambers. Because this is a diesel engine, there are no spark plugs. Instead, the massive 150mm pistons compress the incoming air so violently that it becomes superheated. At the precise apex, the injector atomizes diesel directly into the superheated environment. The fuel instantly and spontaneously detonates, driving the piston down with colossal force. Multiplying this violent explosion across 12 cylinders generates a staggering 38.8 liters of displacement, yielding 500 horsepower and immense low-end torque. But 500 horsepower produces enough thermal energy to melt the aluminum block. Attached directly to the rear flywheel is a massive centrifugal cooling fan. 2 large liquid radiators were wedged into the tight, angled slivers of space on either side, perfectly contouring to the sloped armor. The massive centrifugal fan violently sucks cold air through these radiators, drawing heat away from the coolant before blasting the superheated air out the rear. Finally, the entire power plant was sealed beneath the armored engine deck, featuring distinctive heavy steel louvers designed to deflect shrapnel while maintaining massive airflow. Directly routing from the cylinder heads, 2 crude unmuffled exhaust pipes protruded straight out through the rear-sloped armor plate. When the V2 awakened, the immense torque shuddered the entire 26-ton chassis, transmitting massive vibrational energy through every steel plate. But this 38-liter beast drank fuel voraciously, and with the engine and suspension consuming the entire rear and side cavities, there was a massive volumetric deficit for fuel storage. With the V2 engine consuming the entire rear, the mechanical logic chain forced a brutal compromise. The primary fuel reserves had to be stored inside the fighting compartment. Custom shaped from 2mm thick sheet steel, these fuel cells were internally segmented by perforated baffles. This prevented hundreds of kilograms of liquid mass from violently shifting and unbalancing the vehicle. Bolted directly against the armor plate, these cells sat with virtually zero clearance from the operator stations. A wall of combustible liquid shared the exact same space as the crew. When an enemy kinetic round defeats the side armor, the internal face of the steel violently fractures under the shockwave, generating a lethal cloud of superheated spall. Traveling at supersonic speeds, these 1500-degree fragments effortlessly pierce the thin walls of the internal fuel cells, plunging directly into the liquid diesel. To understand why the vehicle did not instantly detonate, we must look at microchemistry. High-octane gasoline actively vaporizes at room temperature, creating an explosive atmosphere. Diesel does not. When the superheated fragment strikes the diesel, thermodynamics takes over. It instantly boils the microscopic layer of fluid touching it, generating a vapor blanket that paradoxically insulates the rest of the liquid. Without the ambient oxygen required for a flash detonation, the dense hydrocarbon fluid acts as a massive thermal sink, rapidly quenching the steel fragment and stripping its heat. Simultaneously, the sheer physical density of the liquid exerts immense kinetic drag. The supersonic fragment is violently decelerated. By the time it reaches the inner wall of the fuel cell, it has lost its lethal thermal and kinetic energy, dropping harmlessly to the bottom. The fuel itself acted as liquid armor. To extend the operational range without consuming more internal volume, the engineers eventually integrated simple unarmored cylindrical fuel drums to the exterior of the hull. These external reserves were highly vulnerable. They were designed specifically to be consumed during long marches and rapidly jettisoned via a quick-release latch before engaging in direct combat. With the V2 engine fully fueled and protected by both sloped steel and liquid armor, the lower chassis was an unyielding foundation of mobility and survivability. But a foundation must carry a weapon. And here the brutal logic of the sloped armor returned. The extreme angle of the sidewalls severely choked the diameter of the roof opening. Constrained to a 1,420mm turret ring, engineers now had to figure out how to mount a massive 76mm gun into a critically undersized space. The logic chain of the sloped hull created an unavoidable bottleneck. The upper deck was choked, restricting the turret ring to a narrow diameter of exactly 1,420mm. To maximize internal volume and defensive curvature on such a narrow base, welding flat plates was rejected. Instead, engineers utilized a monolithic sand casting process. Liquid steel, superheated to 1600 degrees Celsius, was poured directly into the void. This fluid dynamic naturally formed incredibly thick, complex, sloping curves in a single, seamless piece. As the metal cooled, it contracted into a brutal, unpolished state. The surface was heavily pitted and rough, deliberately left unmachined to accelerate mass production. Casting allowed for variable armor thickness without welding. The sidewalls measured 52mm, while the frontal facing seamlessly swelled to a massive 90mm of solid steel. While the exterior was left crude, the absolute bottom lip had to be precision machined perfectly flat. This smooth rim is what would interface with the hull. To allow several tons of cast steel to rotate effortlessly, the turret rested entirely on a precisely machined race, floating on dozens of large greased steel ball bearings. On the inside circumference, a heavy-toothed gear ring allowed an electric traverse motor to grip and forcefully rotate the armored bell to face any threat. But stepping inside reveals the catastrophic ergonomic cost. The narrow base and incredibly thick cast walls pinch the interior into an agonizingly cramped void. To save critical weight and manufacturing time, engineers entirely omitted the turret basket. There was no rotating floor attached to the turret assembly. When the turret traversed, the operators inside were forced to physically walk across the hull floor to keep up, stepping directly over the main ammunition storage bins. Despite this chaotic environment, the casting succeeded in its primary goal. Molded directly into the thickest part of the frontal armor were the internal trunnion blocks. These blocks were precision drilled to perfectly horizontal alignment, creating an indestructible internal pivot point, capable of absorbing massive ballistic recoil. The monolithic cast steel bell was complete. It was an incredibly cramped, ergonomically brutal space, but mechanically, it was the perfect armored mount. Everything was now in place: the geometry, the suspension, the engine, and the thick cast turret. It was time to install the final piece of the mechanical logic chain, the F-34 main gun. To arm the completed turret, the F-34 main gun was inserted directly through the mantlet opening. But a weapon this powerful requires an absolute anchor. Inside, two massive forged steel trunnion pins were driven horizontally through the drilled mounting blocks, permanently locking the barrel to the cast steel bell. This created an immediate mechanical conflict. The colossal rectangular breech block of the 76mm weapon consumed almost all the remaining free space inside the already cramped turret. To unleash its power, a heavy 76.2mm armor-piercing cartridge is loaded directly into the open chamber. Once seated, the vertical sliding wedge violently snaps upward. This massive steel block seals the breech, locking the explosive energy inside the barrel. At the microscopic level, the firing sequence begins with a spring-loaded steel pin striking the soft brass primer, igniting the chemical charge. The smokeless powder detonates in milliseconds. Because the heavy steel wedge completely seals the rear, the rapidly expanding superheated gases have only one direction to escape. The pressure forces the projectile down the barrel. A soft copper driving band grips the spiral steel rifling, imparting a violent, stabilizing gyroscopic spin as it accelerates to supersonic speeds. By Newton's third law, generating this kinetic energy creates an equal and opposite reaction. The massive steel breech violently kicks backward into the already cramped turret space. To prevent the recoil from ripping the turret apart, hydraulic recuperator cylinders force thick fluid through microscopic valves, converting the multi-ton kinetic blow into harmless thermal heat. As the gun returns forward, the semi-automatic breech opens. Mechanical claws extract the scorching hot brass casing and violently eject it directly onto the steel floor. Because the turret was a sealed, incredibly cramped cast steel bell, the toxic combustion fumes from the open breech instantly filled the entire fighting compartment. To manage this, engineers provided only a single underpowered extractor fan on the roof. In rapid combat, it was entirely inadequate, turning the turret into a suffocating gas chamber. Furthermore, this severe lack of space created a critical kinematic limit. The massive breech physically collided with the low roof and the floor ammunition bins, severely restricting the weapon's vertical elevation. Yet, despite the toxic environment and ergonomic nightmares, the mechanical logic held true. The massive weapon was successfully integrated into the impenetrable sloped chassis. The logic of the sloped armor forced the driver's station to the extreme nose of the tank, while the massive V2 engine pushed the transmission to the extreme rear. Mounted behind the engine was a heavily reinforced, completely unsynchronized 4-speed manual transmission. It was built for absolute survivability, not refinement. Inside, it utilized straight-cut spur gears,